Welcome to the lecture on logistic regression. Last time we talked about naive Bayes, which was the first classifier that we've discussed in this class. Logistic regression is different from naive Bayes because it's a discriminative model. Naive Bayes is a generative model. It seeks to understand what a class is. So if we have an example of cats versus dogs, a generative classifier would like to understand what a cat looks like and what a dog looks like. Whereas discriminative classifiers, like logistic regression, seek to discriminate between samples. So they're trying to identify what makes a cat different from a dog, not to figure out exactly what represents a cat and what represents a dog. For naive Bayes, we wanted to find the probability of a class given the document, but we didn't calculate that directly. We instead used the likelihood that a document was generated given a class, and the probability of a particular class. With logistic regression, we want to estimate this probability of the class given the document directly. There's two stages for logistic regression. There's the training stage, where we find the optimal weights and bias for the particular problem using stochastic gradient descent and cross-entropy loss, and we'll discuss those things in a moment. And then there's the training portion, which is given a test sample X, we want to find the probability of the class given X and return the class with the highest probability. Here we change notation. Before we were using class as C and document as the sample, D. Now we're using X as the sample and Y as the class. This is more traditional machine learning notation rather than computational linguistics notation, so it's the same thing, so don't get confused by that. What are W and B? Well, they're the weights and bias associated with the problem. So if we have all these features for a particular sample, we want to be able to weight each feature depending on its importance, right? And we have this bias that is actually going to be called an intercept. It basically allows us to shift this function depending on a threshold. So if we have our W and our B, we want to be able to make a prediction on a test sample. Our test sample X has many features, Xi from 1 to n. And so all we do is we calculate the element-wise product of the weight with this feature, we sum those, and we add B, which is our bias. So what does this actually look like? It looks like a dot product, right? So we take the dot product of the weight vector with the feature vector, and we add this bias, and we get our prediction Z. Z is not a probability. There's no restriction on the dot product or the addition of the bias that says that Z is a probability. So we need to make some restrictions on this. What do? We actually apply this sigmoid function, which is also known as a logistic function, which is why logistic regression gets its name. The sigmoid function looks like this. It goes from 0 to 1, and this is the equation for it. So it's noted with this sigma. We apply it to Z, and we get 1 over 1 plus e to the negative z. It's a complicated function, but it really just looks like this. And what does it do? It squashes outlier values, right? It takes values from negative infinity to positive infinity and maps them to values between 0 and 1. And what's nice about it is that it's differentiable. So we can take the derivative of at every point, which will be very useful when we're doing gradient descent. Okay, now it's between 0 and 1, but it's still not a probability. So how do we make our predictions a probability? Well, we just do a little bit of finessing here, and we say, okay, well, the probability of the class being 1 is going to be the output, right? It's going to be that sigma applied to the weight times the feature plus 1, which is just this sigmoid equation, right? And then we're going to say that the probability that the label is 0 is going to be 1 minus that value. So now we have the sum of those two probabilities is equal to 1. If we have a test sample, we're going to run it through and we're going to calculate the activation, which is that Z. We're going to apply the sigmoid, and then we're going to say yes if the probability of Y given X is greater than 0.5. Okay, now we understand how testing kind of works. How do we actually do the learning, right? We need to actually find W and B. How do we calculate W and B? Well, we need to think about what we're trying to do. We have some truth, some label for a particular sample, right, which is Y. And then we have some prediction. So we took this Z and this sigmoid and we calculated some prediction, right? So what we want is for those two to be close. So we want the distance between the prediction and the truth to be small. So we use this intuition to create a loss function. Loss functions have lots of different names. They can be called cost functions, optimization functions. It's all the same thing. We'll kind of use them interchangeably. We'll mostly stick with loss and cost functions. In this particular situation, we're going to use a cross-entropy loss. And this is a function that prefers that the correct class label is more likely than the incorrect class label. And this is just dealing with probabilities, right? So all we care about is that the probability of the correct label is higher than the probability of the incorrect label. In this particular situation, we're dealing with a binary classifier. So we only have two outcomes, 0 or 1. So our prediction, like I said before, right, if the probability of the label given the sample is greater than 0.5, then we predict that label. So that's what this looks like, right? It's a piecewise function where the prediction is 1 if the probability that the label is 1 given the sample is greater than 0.5 and 0 otherwise. So this is a piecewise function, which makes it challenging to deal with, right? So instead we can think about this function in terms of a simpler function, where we have the probability of y given x is actually y hat, the prediction to the label, and 1 minus the prediction to 1 minus the label, okay? Why does this work? Well, if we plug in 0, right, if we say that the label is 0, then we get the probability of y given x as 1 minus the prediction, which is exactly what we were talking about before, right? We defined the probability of y given x to be 1 minus the prediction in the case that y was 0. And if y equals 1, then we have the probability of y given x as y hat, which is the prediction, which is exactly what we defined earlier when we were trying to make z a probability and make sure the probabilities sum to 1. We do a bunch of different things. Basically, we take that probability, we apply a log so we can squash it, and then what else do? We also add a negative. The negative helps us to minimize. So before we were trying to maximize the probability of a label given the sample, but now we want to minimize so we can find the minimum, which is easier to do when we're doing gradient descent. So we just use a negative. We're trying to minimize this function, okay? And all we do here is, on the right-hand side, is we just plug in this from the previous slide, and we get this equation here, okay? The details of this are not particularly important as long as you understand kind of the steps that we're taking. So that's for one particular sample. You have a label y and a prediction y hat, and this is over the entire data set. So what is the cost over the entire data set given some weight set and some bias? Well, it's the average loss. So you calculate the loss for every sample given that W and B, and you divide by M, the number of samples, okay? So it's just going to be an average loss is going to be the cost over the whole data set. Okay, now we have our cost function. How do we actually learn? We learn using something called gradient descent. So we need to find the minimum of this function. This thing looks crazy, this function looks crazy, but if you actually write it out with a couple of samples, you can see that it's actually just a function. And if you are in 2D space, you can actually plot it. And what's nice about it is that it's convex, so we can actually find a minimum. How do we find the minimum? Well, we use the gradient. So the gradient is just the multidimensional generalization of the derivative. And the gradient is actually a vector pointing in the direction of the greatest increase of a function. So if you go in the direction of the gradient, you're going to be walking uphill, okay? So what we want to do is we want to go in the opposite direction of the gradient or in the negative direction of the gradient. So this is kind of the idea, right? We have some initial random set of weights, and we just take small steps until we hit a minimum, right? In which case our gradient would be 0. what does this actually look like? We iterate. We just continue to change the weights as we go. So we look at each sample and we change the weights. So that's why we have this T notation. So over time, we're changing the weights. And all we're doing is we're taking our previous weights, WT, and we're subtracting the derivative, right? And what is this little n? It's also known as eta. And all that is our learning rate, and we set that. So it's basically how big is the step going to be. So this is for one particular weight, but if we want to do all of them at once, we actually use a different notation. We use this theta. We'll probably go back and forth between using theta and W and B, but you can think about theta as just containing both W and B. And all you're going to do is you're going to take the gradient of the loss and you're going to subtract it from the current set of weights and bias. Again, you're going to take a step of eta. So eta is some small number that helps you step along. This is the algorithm that's presented in the book. It's pretty nice. It actually has all of the pseudocode, and then on the right-hand side it has, okay, what is that actually in English? So I'm going to ignore all of the setup. You're welcome to review that in the book, but I'm going to start at the theta being assigned 0. So we start with all of our weights and bias being 0, and then we just run through this a certain number of times, and for some reason it's T in this particular situation. And we look at each training sample in random order, and we compute the prediction, okay? So we take our current function and we compute our prediction, and then we compute the loss, so how far off is our prediction from our truth, and then we compute the gradient of the loss, okay? And then what do? We subtract eta times the gradient from our current set of weights, okay? So we go in the direction of the negative gradient, right? So we're heading towards the minimum. So this is called stochastic gradient descent. What does stochastic mean? It just means that we're looking at every sample in random order. So we're adding some sort of randomness. It's really just a fancy term for random. And that's it for stochastic gradient descent. And we use that to learn our W and B. So we just run this a certain number of times until we hit some minimum. And we're looking at one sample at a time. And that can cause a lot of issues, so it can kind of make everything a little unstable. So usually we use what's called a mini batch. So we'll look at 10, 20, 50 samples at a time, and we'll update using the average. And again, eta is a hyperparameter, so we decide what that's going to be. If we take too large of steps, we'll bounce around. And if we take too small of steps, it'll just take us a really long time to get to the minimum. With logistic regression, we're using that particular cross-entropy loss, and that loss function is actually convex, which means we can always find the minimum in that case, which is great. So what is this? What did we learn? Logistic regression is a classifier that's built on some set of weights and a bias, and we fit those weights and bias to our problem using stochastic gradient descent and cross-entropy loss, and we use those W and B that we've learned to predict the class for a new sample, okay? That's it for logistic regression. We're gonna go over some samples on Monday and Wednesday of next week to get a better idea of how this actually applies to computational linguistics. Please make sure to review the perceptron lecture as well. We're gonna use both. You can see how they're kind of related, and we'll discuss that in class on Monday.